Good morning, all. My name is Dr. Deepak Yadav, and today we are continuing our previous complex lecture classes for combinational circuit. We have adder previously, and now we are going to the subtractor part of the combinational circuit in digital system design. So, from the previous lecture, we do most of the circuit design for the adder circuits. Now we come to the subtractor part. So subtractor is nothing but it is somewhat of addition by with the help of 2's complement method. So again, it is of categorized into two categories. Either 2-bit subtraction or 3-bit subtraction. In 3-bit subtraction, there is a borrow that is involved from the next higher bit, next more significant bit towards the next bit, and this is the slide of the half subtractor. So in the half subtractor, only 2-bit subtraction is carried out, and the borrow bit is represented by B out, and the difference bit is represented by D. So as we can see over here, for the 2-bit, the total combination is 4, 0, 0, 0, 1, 1, 0, and 1, 1. And the difference bit is for 0 minus 0, it is 0, and there is no borrow. For 0 minus 1, the borrow is 1. So as we can borrow 1, so borrow 1, for the binary number, the borrow is equal to the base of the system, that is equal to 2. That is, this 2 minus this 1 is equal to 1 over here. From 1 minus 0, it is 1, there is no borrow. And 1 minus 1, it is equal to 1 minus 1 is equal to 0. The difference is 0, and we need a borrow over here for the difference bits. So in this way, we have the difference combination and the borrow out combination for the half adder circuit. So for difference combination, we have two minterms, 1 and 0, and it is represented by x bar y and x by bar. And for the difference, it is again represented by XOR circuit only, x XOR y. And for borrow out, there is only one combination. This is 1, this must be 0. If 1 minus 1, this must be 0. So there is only one bit that is equal to 1, which is represented by x bar into y. So we can say that these are the two output of the half adder circuit, which is having the input x and y. So for the difference, only XOR gate is required, and for the borrow, we need an AND gate and a OR AND gate and a inverter circuit, so that we get the borrow out as the output. So if we talk about the block diagram, it is simple, a block which is having two x and y input and a difference in carry output. So in this block diagram, we have a XOR gate, a inverter, and a AND gate for making the circuit subtractor, half subtractor. Now, if we want to do the arithmetics for the subtraction of two number, as we can take the two number, that is 229x and 46y, and we have to find that difference. So the first step is to convert this number into the corresponding binary number, and the subtraction is done by this. This is the borrow bit, that is the borrow that is carried out by the next bit towards the bit which need the borrow. So if we start subtraction, 1 minus 0 is equal to 1 only. 0 minus 1, this is not possible. So we have to take the borrow from here. So if we take the borrow from the next bit, it is represented by 1. So it comes over here, that is became, this is the borrow is nothing but the base of the system, that is became 2. 2 minus 1 is equal to 1. Again, this bit became 0. Then again we need a borrow which is coming from here, that is 2 minus 1 again, that is equal to 1. So this bit became again 0. So we need again a borrow over here, that is 2 minus 1 is equal to 1. And again we need a borrow, 1, 1, 1, and borrow is over there, this became 0. So this 0 minus 0 is equal to 0, and 1 minus 0 is equal to 1. So in this way we get the subtraction. The result is over there with the subtraction of two decimal number which is converted into the binary, and these are the borrow that is generated during the subtraction process. So for adding for doing this binary arithmetics, we need at least 3 bit to subtract a number. One is borrow, and the one bit is for the x part and one bit is for the y part input, and the difference is created as over here. So we need a full subtractor to subtract this kind of arithmetic subtraction, to do this kind of arithmetic subtraction. So this is the circuit of the full subtractor, in which we have the two input X and Y, and we have the borrow in as the input again, and this is the difference, and this is the borrow out. So for this we need three combination of the input signals X, Y, and borrow in, and it is represented by 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, and 1, 1, 1. So again for this, 0 minus 0 is equal to 0, there is no borrow. 0 minus 0, 0, and this 0 minus 1, we need a borrow. So over here we required a 3-bit, and where the subtraction is performed. So for each bit, like 0 minus 0 is equal to 0, the difference is 0, and then 0 minus 0, again we have the difference 0, and the borrow out is 0. For 0 minus 0 it is 0, and 0 minus 1 we required a borrow over here, so borrow bit became 1, and this 2 minus 1 is equal to 1 is the difference. Then 0 minus 1, again we need a borrow, as well as difference is equal to 1, and then 1 minus 0 is equal to 1, and 0 minus 1 again we need a borrow, then 1 minus 1 became it 0. So in this way we perform all the combination of the input and generate the difference and the borrow out. So for this borrow out and difference, we have the function. For this borrow out, we have 1, 2, sorry, not difference, it is 1, 2, 4, and 7, 1, 2, 4, and 7, and carry out, that is equal to 1, 2, 3, and 7, 1, 2, 3, and 7. So the corresponding difference bit is equal to, it is represented by X XOR Y XOR C in, and B out is represented by X bar Y, X bar B in, and X bar B in. So in this way we have the function of B out as well as difference, and with the help of this we can able to generate a full subtractor circuit as well. Now this is the circuit of the full subtractor. With the help of basic gates, we create the different function as X bar, Y bar, B in over here with the help of three input AND gate. Again next min term, and next min term, and all the min terms are summed up with the help of OR gate. And again for the borrow out, we need an AND gate, and AND gate, and then finally we sum up all the function for the borrow out. If we want to represent this difference function with the help of XOR gate, we can do this as well. This is a XOR gate for X and Y, and this X and Y, XOR of X and Y is given to the B in, to the input of the next XOR gate with the B in, and it generate X XOR Y XOR B in at the output. So we have the combination of difference, and for the borrow out, basic gate is required for generating the circuit. So this circuit is implemented in that box, full adder box, full subtractor box, and we get the difference and borrow as the output of the full subtractor. Now n-bit subtraction. As we perform the n-bit subtraction in the previous slide, the same n-bit subtraction can be performed with the help of full adder circuit as well, because we know how to subtract with the help of full subtractor. The four subtractor are cascaded in series combination, and then provide the input bits and generate the subtraction and the borrow out function. But if we want to do this subtraction with the help of complement numbers, so what we have to generate? We have to generate the second complement of the negative number, and if we add this second complement to the original number, we get the subtraction with the help of full adder circuit. So for what we have to do, if we go for the full subtractor, we have to generate the difference with the help of full subtractor circuit, having like if the number is 4-bit, we need 4 full subtractor. If the number is 5-bit, we need 5 full subtractor. While for doing this with the help of 2's complement number, we require to generate the 2's complement of the negative number. For this, we need an inverter circuit that invert all the inputs of Y, all the bits of Y, and then we need an adder circuit that add the carry, then add the generated carry to the last least significant bit, so that we get the 2's complement of the number. Then we add this X plus Y. It actually perform the subtraction of X minus Y with the help of n-bit full adder. So how this will happen? This is the circuit diagram of the binary full subtractor with the help of full adder circuit. So here we have to perform A minus B, but how it can perform? With the help of 2's complement number, where we generate the 2's complement of B, because B is the negative number, and add A plus minus B, so that we can get the subtraction A minus B over there. So for that we need like if we are doing A minus B, we need to complement each bit of the number B. So for this we need this NOT gate over here at each input of the full subtractor, and one input is same as it is A1, A2, A3 and A4. B0 complement, B1 complement, B2 complement and B3 complement. Then this provide to the full adder which perform the addition, and we require the carry in first input carry C must be equal to 1, because for generating 2's complement we have to add 1 in the least significant bit. So with the help of this we are able to generate the 2's complement of this number, and by doing the full addition with the help of 4 full adder circuit, if the number is 4-bit, we get the sum as well as the carry out at the output. So in this way we are doing the binary subtraction with the help of full adder, cascade of full adder circuit. So this is the adder subtractor, in which the same circuit can perform the addition as well as the subtraction with the help of this mode select pin. If M is equal to 1, if M is equal to 0, this circuit can perform the addition circuit, while if M is equal to 1, this circuit can perform the subtraction for the given number. So if we select M is equal to 0, this bit became 0, 0, 0 and 0, and whatever is going to the input, it is reflected at the output over here, because this is the XOR gate, and the combination of the XOR gate is like this. It is 0, 0, 0, 1, 1, 0 and 1, 1 for this. For 1, 1, this is equal to, for the same bit is equal 0, and for the different bit is equal to 1. So if one of the input is 0, if one of the input is 0, we have the same number that is going out over here. So if it is equal to 0, output is 0. If it is equal to 1, output is 1. As we can see over with the help of this. If this bit is fixed to 0, whatever is the B, it is reflected over here. Whatever is the B2, B1, it is reflected over here. While if we select M is equal to 1, so if the M is equal to 1, the corresponding bit became complement. Like 0 became 1 and this 1 became 0. So as we select M is equal to 1, this all bit became 1. So whatever the input, that is complemented at the output. So it generates the first complement of the number. So if we select 0, the same number is over here and this carry in is again 0, it performs the normal addition as we see in the previous slide with the help of 4 full adder circuit if the number is 4-bit. And if we select M is equal to 1, due to this 1, the input number became complemented over here. So first complement is generated, and for generate second complement we have to add 1 over here. So if we select M is equal to 1, the M is coming over here also. So it generates the second complement as well. So with the help of full adder circuit, we can perform the full subtraction and addition as well with the help of this circuit diagram with the help of the characteristics of XOR gate. Now we have to check for the carry out as well. So like in this circuit as we see over here, we have C3 and C4 that is generated over here. So the problem is that whenever the carry is, this carry is 1 and this carry is 1, the XOR for the 1 1 bit is became 0. This represents that carry out is 0, there is no overflow. If the same 0 is 0, there is no carry is generated at C3 and C4, the corresponding 0 and 0 became create a 0, that is no overflow. But if there is one carry, that is either C3 or C4 is carry, like if this is equal to this bit is equal to 0 and this bit is equal to 1, so in this case due to this the property of XOR gate, there is a carry overflow that is generated over here, and similarly for this one, for this combination, there is again a carry flow over there that is generated over here. So we can check for the carry flow as well. So if we take the example, like we have to perform the addition as well as subtraction for the number 1 0 1 1, and first we have to add like 0 1 1 1. So we have to select m is equal to 0 for this, for the addition, and 1 plus 1 0 carry 1, 1 plus 1 0 carry 1, 1 plus 1 0 carry 1, 1 plus 1 plus 1, it is carry 1, 0 carry 1 and 0, and there is a carry out over here. So for m is equal to 0, if we provide a is equal to 1 1 0 and 1, and b 1 1 1 and 0, due to the property of this XOR gate, the same 1 is repeated over here, over here, over here, over here and over here, 1 1 and 0 over here. So in this way the same number is coming here because we select it, this is became 0. So if x is became 0 for this XOR gate, whatever the number as the input, it became at the output. So we get this same bit over here, and this m create this first carry is equal to 0. Then with the help of full adder circuit, this bit 1 come here, this one over here, this one again over here, this became 0 and this became 1. And when this get edited, we get the output as 0 1 0 and 1, and there is no carry over here. So C3 is one carry over here, and we have the carry out over here as well. So carry out is reflecting over here, and we have this 1 which represent that both the carry became 1, and we have to check this for the overflow for the next coming bits. Similarly, if we want to perform the subtraction, so for performing the subtraction, first we have to take the complement of this number. So let's suppose the number is 0 1 1 0 1 1, and take the complement of this number 1 0 0 0. So how this happened? We apply the same number over here, but due to m is equal to 1, this bit became 1, which create the output as this became 1, which create the output as complement. 0 became 1 and 1 became 0. So this 1 became 0 over here, this 1 became 0 over here, this 1 became 0 over here, and this 0 became 1 over here, as we can see over here. Now for this is the first complement. For generating second complement, we have to add 1. So 1 0 0 1. So for this, this is m is equal to 1, this reflect over here, this became again 1. So with the help of this full adder circuit, these two bits and these bits are added at the first place. Then for the second bit, this adder works. For the third bit, this adder work, and fourth bit, this adder work, and we have the difference, which is equivalent to the sum, that is 0 1 1 1 and 1 0 0 0 1. 1 plus 1 0 carry 1, 0 carry 1 1, and 1 plus 1 0, and there is a overflow carry over there. So the difference is 0 0 1 and 0, and there is a carry over this bit as well as over this bit. So again we check for the carry overflow. This means that the number is as we have the carry, this means that the number is negative, and it is in the complemented form. So what we have to do, we have to take the second complement of this number, the division. That's why we check for the carry out, this carry overflow. So we take the complement of this number and put negative sign in front. So this became 1 1 0 1 1 and negative. So this is the result of the subtraction with the help of this adder subtractor circuit. So in this way, this adder subtractor circuit works, and this is the like description of how the carry out is generated. As V out is 0, there is no need, that is final carry is 0, and there is no need to do any complementing of that number, and if it became 1, then it became a overflow, the result is wrong, and we have to take the second complement again and put negative sign in front. So in this way, this thing is written over here. So in this way we can perform the addition and subtraction over the binary numbers. So this is the basics of the combinational circuit. In this way, if we have to design a very specific circuit for any work with the help of combinational circuit, what we have to do, we have to find out the number of the input required, find out the number of the output required, and how the output are related to the input. We have to find out the logic, and with the help of this logic we have to generate a truth table which provide a combination like x, y and z as the input. Let's see, d1 and d2 is the output, and for all the combination of input, for designing any combinational circuit which is having 3 input and 2 output, find out the relation between inputs and output, like it is depend upon the logic, whatever the logic you are choosing, whatever the problem statement in which you have to take the output corresponding to this input became 1, and you have to take the output for D2 output corresponding to this input became 0. In this way, we have the truth table. With the help of truth table, we have to find out the whatever the minterm is involved in the corresponding output, minimize the values of the minterms or the gate that is required for implementing that circuit with the help of K-map techniques and Boolean algebra techniques. And then after these inputs are outputs are generated, we have to implement with the help of different logic gates. So in this way, this is the process of designing of any combinational circuit. We take the 2 examples, that is adder circuits and subtractor circuits. These are also combinational circuit, which we see how the adders and subtractor circuits or the any combinational circuit can be designed with the help of given inputs and output, as we can see over here. So thank you. This is all for today's lecture. Thanks.